Hi, my name is Rafiqul Islam. I'm a former student of Texas State University. In this video, I'm going to present my research on smart passive ambient control for indoor vertical farming by simulation. So the authors of this research are Dr. Bahrama Shebanpour and myself, Rafiqul Islam. The topics that I'm going to cover in this presentation are introduction, simulation, empirical study, design of experiment, and conclusion. Before I start my presentation, I want to quickly go over a little detail on the facility where my research was done and some research tracks. So my whole research was conducted in Evergreen project, which is an off-grid indoor vertical farming system with subsystem in soil-free agriculture, rain harvesting, atmospheric water generation, natural light and renewable energy collection and delivery, where smart technology systems and their effects on the development of an agriculture STEM education pipeline is demonstrated. Here we can see the overview of the different part of research of the Evergreen, like hydroponic system, simulation of indoor and outdoor natural light, air to water generation, smart capture and control of ambient system, etc. This is the Evergreen and Blue Water project picture on the left and a 3D model of the container of the project on the right. The research area here includes like smart building environment control, solar energy generation, soil-free farming like hydroponic and aeroponic, natural and artificial light plant growth comparison, etc. So that was the overview of the research tracks and scopes of Evergreen. Now I'm going to start with the introduction of my research, which is smart passive ambient control for indoor vertical farming by simulation. So what is passive temperature control? So it is a technique controlling temperature by utilizing environment and the properties of building and by utilizing natural heat transfer like convection, conduction, radiation, evaporation, etc. So the main advantage of passive temperature control is that it saves energy compared with the conventional air conditioning system, and also it keeps the environment green and free of pollution. And indoor vertical farming is growing produce stacked one above another in a closed and controlled environment. The base of this research is to utilize the computational fluid dynamics, or CFD, which is a branch of fluid mechanics that uses numerical analysis and data structures to analyze and solve problems that involves fluid flows. CFD is used to simulate the effect of outside temperature on the indoor air and water through air like forced convection, and container wall, which is conduction, and through solar radiation. Now I'm gonna play a short introduction video of the overview of my research. Hi. Today I'm going to be talking about passive temperature control in indoor vertical farming. Indoor vertical farming saves land, saves water usage, and reduces cost. But the problem with indoor vertical farming that it produces a lot of heat for artificial lighting, and it requires air conditioner to cool down the system, which increases the energy cost. But the energy can be saved by implementing passive temperature control. In my research, a computational fluid dynamics simulation model is developed An empirical study is done to design a smart passive temperature control system which will control the temperature for indoor vertical farming and reduce the cost. Okay, the simulation of my research will include methods and material. Under methods and material, there will be flowchart, geometry, initial and boundary condition, adding physics, adding mesh, and adding study and running the simulation. After that, we will do CFT. We will have CFT result. Then we will validate the result and analyze the result. This is the flowchart of my simulation. It starts with defining the problem, then creating geometric model. After that, we set up initial and boundary condition, and then add physics. After that, we create mesh, and then create time dependent study. After that, we run the simulation. If the result from the simulation is verified, then we go to validation step. If not, we go back to the setting up initial condition and continue from there. So if it's verified, then we validate, and if it's validated, then we collect the data and do the documentation and reporting. That's the flowchart of the methods and material of the simulation. And in the simulation, I used COMSOL multiphysics software. First, I set up the geometry. In this case, we have container wall with 3 layers of sandwich material where 73 mm polyurethane is sandwiched by 2 mm aluminum on the both sides. Next, I set initial and boundary condition by setting up the environmental condition from local weather station, and then with the orientation of the container as well, because it affects how the sunlight or heat from the sunlight radiation affects the container. Then I added two physics condition. First one is heat flux to consider heat transfer with convection and conduction. Then surface to surface radiation to consider solar radiative heat transfer. Then I had to add mesh to define the precision of the simulation. In this case, I chose fine as a meshing precision. Finally, I added time-dependent study with 1 hour interval to take data and run for 72 hours. So this is the simulation result. Ambient temperature and solar radiation affects the container surface differently at different time of the day, as we can see here from the pictures. Like in 6 p.m. It affects in a way that is different from the 12 a.m. in the midnight. So this is the result from the simulation. So for validation, I compared with the simulation data with the actual data that I measured in the container, and I compared the simulation data with the actual data with a paired t-test with 95% confidence interval in Minitab, which shows that 0 is included in the confidence interval of like minus 0.3 and 0.4. So there is no significant difference between temperature data from simulation and actual data. And so we verified the simulation, and so the verified simulation model will help to run the variety of scenario, determining time to transfer water from outside to inside to save the energy, designing passive temperature control system, and save the energy. Now the design of experiment part, which will contain the overview of the design of experiment, methods and materials, and result and analysis. Uh, Now let's begin with what's DOE. It's a series of tests with purposeful change in control factors to identify changes and determine optimum condition. So there are different types of DOE. Most commons are one factor design, factorial design, and response surface method. Under factorial design, there is two methods, full factorial and fractional factorial. This is the flowchart of the design of experiment. It starts with data collection, then choosing the method and running the experimental runs. If there are too many runs, we use a fractional factorial design. If not, we do the full factorial, but in our case it's too many runs, so we chose fractional factorial design. Here are different factors and levels of the experiment. Here we can see the factors are water in gallons, duration in hours, and the different time of the day to start the experiment, and there are three levels. So the reason I chose the fractional factorial design, because with three factors and three levels we have 27 runs, and fractional factorial design has reduced it down to like 9 runs. So this is done with Taguchi design method in Minitab. Here is the runs from the simulation with three levels, which are 50 gallons, 200 gallons, and 400 gallons. Here is the data table found from the simulation to analyze average temperature difference to find the optimum condition. And to select the optimum condition, considering the summer and overheating, for transferring the water between outside to inside reservoirs, the following conditions are, these conditions are required, which is like water, the amount of water higher the better, the temperature difference negative and larger the better, and the pump energy lower the better. So from the previous table we found out the optimum condition is 400 gallons of water. Transfer time is between 4 a.m. and 8 a.m. and the temperature difference is also high in this condition. So finally, in this research, a CFD model is developed to determine the indoor air and water temperature at any given time of the year, and the model is validated with experimental data. And then an empirical study is carried out with 8 different experiments with different weather condition and different lighting condition, and found out how different weather and lighting condition affects the water temperature. So that's all from my research presentation. Thank you very much.